I'll let you start.
Perfect.
All right. Hi, everyone. So this is a group who's meeting for going over the pharmaverse packages, especially for those who are seeing this video after the fact. We are a group of folks from DSLC group. We are talking about pharmaverse examples, the documentation that's available online. And today we are going to cover the introduction, starting with ADSL and so on. Over to you, Julián.
Okay. Hello, everyone. I'm Julián. And we're now just going to talk about how to go from SDTM to ADSL. But as I come from the finance industry, so I have no idea about all the acronyms in pharma, and as it is very sensible data, you have everything very well detailed, but it's a bit difficult to catch up. So I'm going to start by doing a very small introduction to CDISC and how you work with clinical data. So what we're seeing today is just this very quick intro to CDISC, which is going to be this presentation. A bit more in depth about the SDTM and ADAM data standards with a focus on ADSL, which is what we're going to be deriving today from SDTM. And then we're just going to treat this some sort of as like a workshop, following the pharma examples quarto document that is on the pharma examples website. So okay, I suspected it, I didn't know it, but of course, clinical data is very complex. You have a lot of, you have the patient demographics, lab results, drug exposures, adverse events, efficacy outcomes, and many more things that you have to take into account. And because we're talking about human lives, the data must be accurate, it must be traceable, consistent, and most importantly, it has to be reviewable by the FDA or EMA or any other drug administrator. So the issue with the clinical data was that every company would format data differently if there was no standard for it. So the regulator said, okay, use this standard format. And this standard format will be CDISC. CDISC stands for Clinical Data Interchange Standards Consortium, and it's a non-profit global standards body for clinical data. And it standardizes both how we collect the data, how we structure it, and how it has to be submitted for all the clinical trial data. And it ensures consistency, traceability, and compliance with regulators. Okay, this could be a big picture where we have we first have a plan, we then have to collect the data following some guidelines, then we organize that data into different domains, and then we derive the final data set to be able to do the analysis, and then we do the submission. There's so many acronyms in pharma that it was quite difficult for me to catch up. You're probably going to see me consult things as I go during the workshop or during the example, because it has been very difficult for me to remember what most of these stand for. So the first thing, the PRM is the protocol representation model. It defines the study objectives, the endpoints, the population, the visits, etc. And it's like the foundation for everything else. So it's like the model for everything else. When you have to collect the data, the standard that is used is Clinical Data Acquisition Standards Harmonization, or CDASH, and it tells you how the data has to be collected. So when you have to you have to create the fields that need to be filled when doing a clinical study, these case report fields are built following this standard. Once you have collected the data, we have SDTM, which is the study data tabulation model. This represents the standardized but raw data. So it's not yet analysis ready, and it's divided into domains. More on that later. And the ADAM, the analysis data model, it's derived from SDTM, and it's already analysis ready, and it's clearly structured, and it can be easily traced. And it's the one that we later use to create the statistical outputs. Today, we're not going to do the analysis, but what we're going to see is how to go from SDTM to ADAM. More specifically with the ADSL dataset, which is one of the many ADAM datasets that there are. So, okay, I'm going to go a little bit more in depth into what SDTM and ADAM are. Probably many of you already know this, but it was a bit important for me to at least get the general idea of it. So the SDTM is the data, the raw data, once it has been already structured from the collection. It's usually organized into domains. Its domain is like some sort of data set of its own. For example, the DM domain, it's the demographics domain. They are always specified with 2 letters. The AE is the adverse events domain. The VS, vital signs, EX exposure, and there are many more. You can see a lot of sample data sets with the pharmaverse SDTM R package. It contains a lot of different examples, and we are actually going to use some of them as base to then derive the ADSL dataset from this. So, for example, this is what a demographics table would look like, a very, very simplified one. This would be three individuals, and it would have information about an individual subject ID, the sex, the age, a different way of the age units, the race, what arm of the study they are, if, for example, if they are on active treatment or they are in placebo. There can be many more columns than this, but this would be like to get the general idea of what an SDTM table looks like. Then we have ADAM, which is the analysis data model, like I told you, and ADAM can have many different dataset types. We're going to see the ADSL one, which is the subject level analysis dataset, which contains 1 row per individual that's going to be participating in the clinical trial. And then there are many more, and these are the ones that we're going to be seeing over the next weeks. The pharmacokinetic concentrations dataset, pharmacokinetic parameters dataset, response dataset, time to event dataset, vital signs dataset, and adverse events dataset. And they are also important, but for different things. So the ADSL is like sort of the core ADAM dataset that contains 1 record per subject, as I just told. And the purpose is to provide several information about its subject, like the demographics, like the treatment that has been assigned to that subject, the dates of the study, some flags that for the population, and many things that can be needed for the later analysis. It's very important because it acts as a central group and it can be later merged with other ADAM datasets to do other types of analysis. And it's required also for traceability and regulatory submission, because this one is directly derived from SDTM and metadata. This is also a very, very simple example of an ADSL data. This would be two individuals. One that has taken a drug called hypertensive, and another one that hasn't taken a placebo. And you can see that some of the demographics can directly be derived from the AZTM demographics dataset that you saw like before, like sex, age, or the age units, and then many more other columns that can be also derived from different AZTM domains. sometimes directly, sometimes making some aggregations or sort filtering. Okay, so when deriving from SDTM to ADSL, the main input sources are the SDTM datasets. Then also some metadata. This, I have to say, it's something that is not super clear to me because I don't know much about what the metadata looks like in pharma. But apparently, usually you work with some sort of define.xml file. And in this case, what we're going to do is we're going to use a metacore object, which is just an object in R that contains a quite well structured metadata for many of the data sets, many of the variables, and much more. Okay, and then our goal is to create one record per subject, per each subject ID, with some of the key analysis variables, like demographics, treatment assignment, population flags, study dates, and some other certification factors. So the way we do this is we either have like a direct copy from the data set, like it's the case for some demographics, for example, age, sex, and race, or you can also derive them using some documentary logic. Like, for example, you may want to aggregate age, for example, from 0 to 18 years old, from 18 to 64, and from 64 onwards. So that way you are using the age, but you are doing some aggregation. So and the same with sex or race or many other columns on some of the SDTM domains. So, for example, this would be from the first table that I showed you from SDTM demographics. We can directly derive some of the columns in the ADSL dataset, and some others need a bit of transformation. For example, if you see the arm, you see that in the SDTM it's just active treatment or placebo, but then in ADSL, it has a different name, the column, and it is a bit more specific. And what it does is it has used a bit of the metadata combined with the SDTM, and with some transformations, you create this new column. So what's going to be today's workflow? Okay, we're going to first load the data and the required pharmaverse packages. And then we're just going to start building some of the derivations. So, for example, we're going to first start with the variables that can be directly copied from SDTM domains. Then we're going to have some grouping variables by some categorized subjects like age or region or race or whatever. Then we're going to have some exposure derivations, which, for example, we're going to derive what the treatment start and end dates were. Then we're going to see some treatment variables, like the planned treatment versus the actual treatment, some disposition variables, like the study status, if it's completed or if it's discontinued. Derive also the cause of death, like the death, like the flag of it, or the date or the cause, and many other grouping variables. And finally, we're going to apply the metadata to create an XPT file and perform some checks to see that we are compliant. Okay, the main packages that we're going to be using are metacore, which is an R package that it allows you to create an object that contains all the metadata, and it acts as a single source of truth for metadata. Then meta tools that using a metacore object and the metadata, you can automate and check some parts of the dataset construction. The pharmaverse SDTM library that it has some examples of some example SDTM datasets, which are the ones we're going to use to then derive the ADSL dataset. Admiral, which is one of the most important libraries for deriving any Adam dataset from SDTM domains, and then the exporter library that it converts the R data frames into SAS transport files, because these are required for the FDA submission. Okay, so let's get started. So question, do you have RStudio in your computer right now? Are you able to like download a repository or? Okay, I see that ID says yes. And you have the option to run everything locally, okay, like opening RStudio, downloading the repository directly from the pharmaverse examples. You can either download it as a zip file, or if you use Git, you can simply clone the repository locally. Then you can, once you have this downloaded, you can set the working directory to the correct directory where you have downloaded the repository, and we can follow the instructions on the pharmaverse examples website to do this. So you can either download the repository as I told you, and just run this snippet of code that will install all the dependencies required. Or another option is to just, if you don't want to install anything, or you don't have access to RStudio right now or whatever, you can simply click here on the Exposit Cloud, and it will open an RStudio instance for you with all the necessary files already and all the dependencies already loaded. So you can follow along with this or with all things. I'm going to do it locally because I have already everything set up, but it should be pretty much the same. Okay, so is everything clear overall right now? Do you need maybe we can give some minutes for everyone to like set things up and everything?
For me, you can go ahead, Leon. That's fine.
Is it fine? Okay. Okay. Then let's go for it. So I'm going to open my RStudio. Can you see it correctly? Like is the size of the
Yes.
Okay.
Yep.
Perfect. The size of the text. Yeah, enough. All right. So let's get started. All right. So I'm going to go through this as if it was the first time that all of us are going through it, because it's quite dense, and I'm just going to follow along everything, and just every time that something new pops up, I will try to explain it or even to remember what it did with you, because I haven't had much time to go through it many times. I have gone through all the code 3 or 4 times, and still there are some things that I need to refresh myself at the moment. So let's go. Okay, so as I told you, we are going to go from some SDTM examples to an ADSL dataset. And for this, we're going to be using the libraries or the packages that I have already described for you. Some of them are quite complicated, and it would probably need a full session just to explain one of those. But we're going to just see we're going to only look at the functions that are going to be necessary for the example. And maybe later you can on your own time dig deeper, because this is quite dense, as I told you. So okay, what's the flow for today? We're going to start by simply loading all the packages, and as using the we're going to have some of data sets from the pharmaverse DTM library. Let me show some of them to you so that you can see how they look like. Like, for example, the demographics, we have, as you saw on the simplified example, an individual subject ID, and many more columns, for example, the age units, the sex, the race, the ethnicity, the arm of the study, and some simplifications of the arm of the study. We also have many more other data sets that we're going to be using one by one for deriving the ADSL dataset. So, okay, we're going to be using for the beginning, the demographics and some supplementary material for the demographics. Oh, yeah, sorry, I forgot to mention that when SAS datasets are imported into R, mainly using the Haven library, the missing values, instead of adding an NA, they are added as empty characters. So this is a bit not optimal for the study. So what we do first is to convert the blanks to NA. Then we're going to use a function from the MetaTools library to combine the demographics with some supplemental information for it. This is in long format, so instead of having to transpose everything and do it manually with tidyverse or dplyr functions, we already have this combined function that's it for us. From time to time, when a new function arrives, I'm going to click F1 on it so that we can see the official R documentation on it. So in this case, you can have it, and maybe if you didn't know that when you're in our studio, you press F1, you see the help for that function, and if you click F2, you can even see how the function looks like on the inside. Maybe for now, we are probably not going to need to use F2, but maybe F1, it's going to come handy. Then we are going to combine these two data sets to get a combined demographics with some supplementary material. And now we have it. And then we're going to create our MetaCore object. Before diving into this, I'm going to give a very quick introduction to MetaCore, because it's a bit dense. So as I told you, the MetaCore is just an object, an R6 object, more specifically in R, that contains the metadata. It has a very specific structure. So it has dataset level information inside the DSSpec dataset. Then it has some rich dataset that combines the specification for the dataset with the specification for the variables. Then we also have value level information. It contains all the derivations, like how everything from LCTM has to be derived to the ADSL, and much more information. If you want to dive deeper, just check the official documentation, because it's also a bit dense. So yeah, we're going to create our metacore object using the expect to metacore function, where you pretty much put the path to some sort of metadata you have. In this case, it's an Excel file that is on the let me check. Yeah, that is on the examples on the metadata folder. We can see a bit, if you want, about the file. It's just a lot of different sheets with some columns on them with a lot of metadata. I'm sorry that I cannot go much more in depth into this because it's quite dense and I actually don't fully grasp it myself yet. So what you have to know is that we're going to convert this metadata and put it inside an R object that has a defined structure that it can later be used by other functions from both the metacore library and the admiral library to derive some ADSL columns. So let's go for it. And now we have everything saved into the metacore. Okay, now we can finally start building some of the derivations. The first, what we are going to do is to pull all of the columns that come directly from the SDTM dataset. So in this case, all of the columns come from the DM and the supplementary DM datasets. This is a bit tricky because we have already combined them into one single dataset, the DM sub DDM. But this function requires that you specify you need to reference both of the domains as the provenance of the variables. So we have to put it like this, in the form of a list, where we say that the DM is the already combined and the sub DM is also the already combined. If you want, we can see the function here. So what we need is the metacore object, the list of the datasets, and if we here, in this case, we have to say that the predecessor only is false because we have already combined them. And to see what this first what this looks like, we can see we can print here with the printdf. Printdf is just a helper function from the examples repository that it simply uses React table to put in a nice HTML format the data frame to be shown more neatly. So now we have our base ADSL dataset with only where we have only derived the SDTM variables that can be directly copied from SDTM. Now we are going to go and start deriving some variables that are grouping variables. For this, we're going to use the admiral library, and we're going to use mainly this function, which is the derive vars cat, which basically is used for derive some categorization variables, like for example age or race or other things. And what this function needs is it will need some base data set like the one we have just created. and then a list of an expression that that tells you what are the aggregations that we need to make. So in this case, we are going to create two new variables, which is going to be the H group 1 and the H group 1M. And for this, we're going to be putting a condition into the H column that already exists in our data set. And we are going to go through some conditions for it. If you are not familiar with this kind of syntax, it's the same syntax as if you're using the dribble function from dplyr or from table. This what it does is that you are creating some sort of data frame, but you're doing it line by line in this case. So you put here like the name of the column name, and the first row is the column names, and then you just add the rows with a comma separation between them, and that's pretty much it. So in this case, we have the first condition to see if H is not non-available. No, sorry, if it's non-available, and we will assign it missing, or in this case, the group number 4. Then if H is less than 18, we assign this label or this label. If it's between age 18 and 64, this label, or this group, sorry. And finally, if for everything else, that we just add that it's plus 64. Okay, this is the way to do it with ADSL, but there are many more options. So we are going to see 3 options. This is the first one with the derived var_scat function. And this is what it would look like. So you can see that it's once you more or less understand what the function does, it's quite concise and it's quite fast. Apart from this option, we can also use our metacore object, our metadata, and see the control terminology for this. Because as these data sets are all standardized, you can simply check the metadata and create a categorical variable using that metadata. So in this case, what we are going to do is we use the grouping from H group 1 and just add it basically. So this function needs the data set, the base data set, then the metacore object that has all the metadata, the reference variable that we're going to use, and then just the grouping variable. And if you want a number coded variable, you can also add it here with this variable. And if we do this, it will output the exact same output than the other one before. And then a third option would be to simply use custom functions. So instead of using these two libraries, you can create your own custom function and just say that, well, using case when, which is a pretty standard R function, you tell it the condition and the label for that condition. We do one for the H group 1 variable and another one for the H group N variable, and it would just using mutate from the dplyr library. We would just create the same data set. These are all the same data sets, so it would look also the same. So these are the 3 options for grouping variables. Maybe as everything is so standardized, it's usually quite easy it's probably easier to derive it using either Admiral or Metacore libraries. But just so you know, you can always use some custom functions also. We can also do the same with the race instead of the age. Pretty much, we can use the control terminology, like we already saw with Metacore, or we could also do it with the other two options that I saw you. But it would be the same. It would be the same process, just adding some condition and adding some. And adding the groups like that. Okay, so now we have finished with the grouping derivations, group variables. We're going to see now the exposure derivations. Here we're going to be deriving mainly the treatment start and treatment end dates. For that, there's a function from Admiral that derives date time variables. One thing, because at this point I was already pretty lost on the names of the variables for the ADSL. So one very useful website is this one. That maybe I can even send it to you over Slack. Here you have the names of all the variables or parameters for any Adam data set, and which you have a small description of what this acronym means and the most useful function to derive that column. So it comes quite handy when you're working on with your own data and you're not sure how to derive one specific column. You can check this website, and you can even look for it with these text forms, and you can get this, and you can even take a look at a template example for it. Okay, so moving on. So these are the exposure variables. Here we are going to use the derived vars DTM function from the Admiral library, and here what we're doing pretty much is we're going to impute this column from the EX example. EX is a domain from SDTM, and we just tell it what the name of the new variable is going to look like. This what it does is that it will always add this prefix and then the date time acronym to it. So we're going to create the EXST DTM column here, or the EXEN DTM. Let me show this to you first. So this would. So yeah, this will look like this. The end date and the beginning date. So then we're going to continue from where we ended up with the grouping variables. So we already have the variables that can be directly derived from SDTM and the variables that are derived from grouping variables. And now we are going to use the derived pharmaverse function from Admiral. And what this does, it adds new variables to the dataset based on the variables from an external dataset. In this case, we're going to use the EX domain, which we added a couple of new variables to it. So we have the EXT dataset now, which is an extension of the exposure domain from SDTM. And then we just add adds a filter to it. In this case, we are going to see that the dose is higher than 0, or it's equal, and it contains the placebo string inside of its name, and it's also not an NN. And we're going to create some new variables with it. We also have to give this an expression of what the new name is going to be, and what variable is it based from. So yeah, I have to remember once. Yeah, you can just sort the order in which they will have to be output. And we're going to do this for some of the variables. So in this case, it's going to be the treatment start date and the treatment end date. And as I don't remember what these are, I'm going to look at them. Okay, so it's the start time imputation flag in this case. As you can see, there's many acronyms for everything, and I have been trying to keep up with everything, but most of the time I'm just copy pasting things here to know what we are talking about. So once these variables are derived, we are going to derive the start date and the. So it creates the date output for datetime variables, and it just uses the source bars for it. And pretty much we have the treatment duration as well in days, and just merge everything together. And when we do all of this, we get all of these new columns. So pretty much, I know this is very messy and there's a lot of names, but what we're pretty much doing is we're taking different domains from the SDTM dataset, and usually you know what columns you're going to need for your analysis. So the workflow here would be to check, for example, this column, and look at what admiral function you need to derive it, and pretty much follow the documentation of that function to get a new derivation, to get a new column. This is quite messy at the beginning, but once it's all set up, it's pretty much automatic to convert from your SDTM dataset to your ADSL dataset. So far we have gone through the grouping variables and the exposure variables, and now we're going to go to the treatment variables. Okay, so what we're going to do is we can simply map them as we see fit with a very simple mutate where we add the name of the column, and with a simple if else we can create this new variable. So it would be just to create this treatment, it would be placebo, and in this case this Shannon line treatment. Okay, so yeah, okay, so we're now going to use the MetaTools package, which is another library from R that what it mainly does is to take your metadata from the MetaCore object and create a new variable using the code list inside the metadata. So we need the metacore object, our input variable that we just created here using mutate, and the output variable, which is pretty much the just a group number. So in this case, we are associating one number for its different kind of treatment. Okay, so this was more or less simple to do, just doing the mutate and then using the metadata to add a group, to assign a group to it. Now we're going to derive disposition variables, which mainly will come from the disposition domain from SDTM. So for this, we're mainly going to use the function from Admiral, derive parse DT and derive parse merge. Yeah, we are going to convert this disposition date to a numeric date. And then we're going to extend the DS dataset using this numeric date, because we're going to need this column to later derive some more ADSL variables. So first, it's very similar to what we did in the exposure part, which is we take the SDTM domain and we extend it a little bit with some new variable that is more similar to what then is needed in the ADSL dataset. And then we derive the ADSL variables from there. In this case, we take the dataset DS, we create we create the new variable here, and we derive it from this variable here. And then using the derive parse merge, again using this external dataset, we do it by each of the subject IDs, and we create a new EOSDT variable based on the one that we just created before. And we can add a filter where we say that this variable it's just the disposition event, and the code is not a screen failure. Have to admit, I have no idea what this means, but it's just that you can see that you can add filters to improve the derivation of the variables. Okay, so now this function allows to impute partial dates as well. If the imputation is needed or missing days are to be imputed to the first month and missing months to the first month of the year, we can set the highest imputation to equal m. And as we saw, yes, the end of study status is based on these two variables here, and it can be derived using this function that I just told you. Okay, so we can have an example function for deriving this variable, and with the case when, as we saw it in the other time, you just put the condition to the left and the label to the right. And now we can pass this custom function here to the derive parse merged, and directly using the same syntax as we use here, directly derive these new columns, and we end up with this new with these two new columns for the dataset that are also needed. Okay, this is getting quite dense. Yeah. Sorry, I think I somehow missed some part of this of this part of the example, and I somehow skipped part of this, but let's try to see it together nevertheless. So we're going to now get the imputed death rate using the same variable as before. As you can see, there are many things to derive the variables from the for an ADSL dataset. The main and we are going to do pretty much the same all the time. We're going to use this function. We are going to add the prefix that then it will add date time to it. We take what we need from the other data set, and just fill everything in the function as we need it. Okay, I see that we're getting out of time, so I'm going to just run through everything as fast as possible. We are going to just derive many more variables from using the merge, which means that we take an external data set, in this case the extended DS data set, and we add some new variables to it. So it's pretty much the same all the time. The workflow is always the same. You just check what function you need. You follow the documentation for that function, and you just derive wherever you need. In this case, we are also going to derive the duration relative to death, like the relative day of death, for example. And we just get the new variables. Okay. Yeah, now that we have it, the randomization date here, we can also derive a population flag. We create a custom function that if it's missing, we just add a yes, or if not, an NA character. And here we would have like all the derived data set. I think that we're getting a bit quite late now, so okay, there's not much to go through yet, but we're not going to derive the cause of death. We're now going to use a bit of a different function here, which is the derive extreme event. And this, what we do is we add the first available record from the events for each group as new variables, and all variables of the selected observation are going to be kept. So it's a bit similar to the DT1, but with slightly different needed variables. Sorry, I'm going to go very quick to this because I have to go very soon. I thought I was going to be a bit faster, but this is taking much longer than expected. As you can see, this is we can derive other grouping variables using the same syntax that we use for the age and the race, where we just add an expression with the condition and our new variables. and the labels assigned to that condition. And then yes, just using the derived vars by category, whereas as the ones from mates and race, we just add them. And we just have the pretty much the completed ADSL dataset with all the types of variables, like the grouping variables, exposure derivations, treatment variables, disposition variables, cause of death, and some other grouping variables. And now all we have left is to add the metadata to create an XPT ESUB file, and just perform some of the text to check that everything is ready for the FDA to test it. And pretty much that's everything so far. So this would be it. I know it was very dense, and that in the end it got very messy. But as I told you, I'm not an expert in pharma, so I did what I could, and with a very limited time that I had to prepare this. So yeah, thanks so much for attending, and if you want to ask anything, feel free, please, or to add any comments to it.
No, well done, Julián. You
Yeah.
have mastered and grasped a lot of the concepts in a very short time, so I'm very impressed.
Thank
Yeah,
you.
very nice.
Thank you. Thank
Will
you
you
very
also
much.
merge your Quattro slide to the GitHub branch that John shared?
Sorry. Oh, I see that there are many.
No, it's fine. It's fine. I was just wondering how to do that. I'm a beginner to Quarto.
Mhm.
Yeah, that's very nice, and I think very well done. Is a really good kickstart of this book club.
Thank you. Thank you. I really think that I need to still study a lot, because all the acronyms got me sweating, because there are acronyms for everything, and I guess that once you have several years of experience in pharma, you already know many of these variables. But I just wanted to at least be more or less clear on that. It's not that hard to do it in R. It's just you have some functions, mainly from Admiral and Metacore libraries, and you just check what variable you need. You see what is the assigned Admiral function to it, and just follow the instructions, which are quite clear, and they help me a lot actually to understand.
Yeah, Jim also.
Thanks, Jim. I had to do it over the weekend, and I thought I was going crazy, and
Yeah.
I almost said I almost told I was about to let you guys know that I wasn't ready to do the presentation, because I felt with an imposter syndrome so big but thanks for appreciating it. I know it was quite
Yeah.
dense, but I think this topic is quite dense by itself, so
No,
yeah,
and of course we will have the functions repeating. And I think what's very key for me, what was very valuable, is the F1 and the F2 functions. I mean, pressing the F1 and F2 buttons
yes.
and seeing the code. So that's very nice. Because I think currently in our company, we are also thinking to implement pharmaverse, but then the question is, yeah, isn't it maybe easier to work with our tidyverse? Why should we?
Yeah, that's true,
because
because
it makes more sense.
it's quite straightforward in the beginning, but I think that once you start understanding these functions from the pharmaverse, it's much faster to do it using these pharmaverse functions than just the tidyverse. The tidyverse allows to be much more customizable, and probably for some variables maybe, or for some groupings or aggregations, it's even easier to do it with the tidyverse. But for example, to work with metadata, because I'm not sure how do you work with metadata in your company, but creating a metacore object from your metadata and then using that to derive many columns, it's quite useful as far as I can tell.
Yeah, true. Jim, you had something to say? Did you raise your hand or?
No, nothing.
Okay.
But I do second what Julian just said, that you can do it in tidyverse, but the Admiral takes care of a lot of the little details for you.
Mhm. Yeah, I think
Yeah, right.
it's harder to like to mess up if you use Admiral. Like if you are, for example,
Yeah.
using tidyverse, it's much easier to add something that is not exactly right for the FDA, and you messed up that step. And Admiral, it already automates many of the steps that you're going to be having to be done using tidyverse.
Yeah, I think one of the time-saving functions I find the date imputation functions, where you can choose if you want to set it to the last day of the month or the first day of the month. But then I did not check if you can set something also to the 15th of the month. So how do you customize them? Yeah. Oh, thank you so much. I think you also had another appointment, right? Yeah. See you next week then.
Perfect. Yeah, see you next week. Okay.
Okay, thank you. Have a nice day.
Perfect.
Bye-bye.
Have a nice day. Goodbye.